Okay, so welcome everybody for tonight's talk. Today we have Ilaria, and she was going to talk about explainability with knowledge graphs. What have we learned? This is the talk series of the cost action on distributed knowledge graphs. We've had a few talks already. You can watch them in our YouTube channel. And we also have a few talks coming up on January the 31st. We will have a talk by Mayank Keriwal. On March the 4th, we will have a talk by Mark Newson. And on April the 17th, we have a talk by Peter Patel-Schneider. What is this cost action? It is a European research network where more than 30 countries are represented. We run workshops, hackathons, and short-term scientific missions, for which also you can apply. This overall runs from 2020 to 2024. So we have a few months still on the project, and we are now in our final year. This is chaired by myself, this cost action, with Axel Polares as a vice chair. We have Michel Dumontier and Remzi as working group leads next to Andreas, Antoine, Olaf. Then there's John as a scientific representative of the grant holder, Anastasia Dimou as the science communication manager, and Stefan Gostojic as the grant coordinator. So much on the cost action. Today we have Ilaria, and I would like to hand over to Olaf to announce the speaker.
Yes, hello and welcome from my side as well. I'm very happy to have Ilaria as a speaker. She got her PhD from the Open University in the UK. And the title of the PhD was Explaining Data Patterns Using Knowledge from the Web of Data. And for that PhD, she received this Distinguished Dissertation Award of the Semantic Web Science Association of Swiss. She got this award in 2017. And as you maybe know, we run this talk series with speakers who received either this dissertation award or they received the 10 years award of Swiss. So now Ilaria received this award in 2017. 1 year later, she went to Amsterdam, to the Vrije Universiteit in Amsterdam, where 2021 she became an assistant professor there, that she still is. She has been involved in several conferences. She is the editor-in-chief for the CEUR-WS workshop proceedings, where many of us probably publish their proceedings of their workshops. She's also in the steering committee at the moment of the Hybrid Human AI conference. And her research, the focus of her research is on systems that combine semantic technologies, open data, machine learning, in order to generate complex narratives with applications mostly in scientific scenarios and in robotics. And if you look at kind of her most cited papers, many of them have the word explain or explanation in their title. So I'm very happy to have her here and kind of reflect on the work that she did in her PhD and what has happened since then with this work. The floor is yours, Ilaria.
Thank you so much. Thank you for Olaf and Tobias for the introduction. Yeah, I'm going to share my screen. So my question was whether you were keeping the rights. Can you just give me a sign that you can see that, I think. Okay.
Works.
Yeah, great. So good evening or good morning, everybody. My name is Ilaria Tiddi. I work at the Vrije Universiteit in Amsterdam. I'm an assistant professor. I'm very, very happy of giving this talk today. That was really a nice opportunity for me to reflect on the overall research that I've been doing in the past since I was a PhD student. And of course, it's about explanations, which is a very hot topic in these days. And really, my work and my background is on knowledge graphs. So I've been working most of my life on how to use knowledge graphs in the context of generating explanations. And that's what we are going to see a bit. Just to, Olaf gave a very good introduction of myself. As I said, I'm an assistant professor on hybrid intelligence. My background is on knowledge representation, knowledge graphs for explainable AI. These days, I'm mostly focusing my use cases around hybrid intelligence. You will hear a bit more later on. Knowledge representation-driven robotics, and also scientific assistance and scientific discovery. There's more about me. You can check on my website. This slide is actually wrong. So it's ISWC 2017 that I missed. The one when I was about to supposed to come on stage and receive the ESWC dissertation award. I was actually driving to a very far place, so I had to miss the conference. But I was very happy of receiving the news nevertheless. So to give you an overview of what this talk is going to be about, I will be describing a bit what the work during my PhD was. So as you heard from Olaf, the title of my thesis was on explaining data patterns using knowledge from the web of data. And then I also want to discuss a bit what has going on since then. So since 2017, 2016-17, how explanations have developed, how knowledge graphs have developed, and the overall area, and also and concluding with some future consideration. Where do we want to go, and how can we go from here? Starting with about 10 years ago or a bit more, it's always hard to realize it over 10 years now. I like to show these pictures to warm up a bit the audience. I'm not sure I can actually see the chat, but maybe somebody wants to. I like to ask the question on whether somebody knows this picture, which it's quite famous, used to be quite famous. I don't know whether somebody is familiar with that. And this might be hard. I don't really see the chart, but that's okay. So this is a typical knowledge discovery process, as was firstly introduced around in the middle of the 90s, when knowledge discovery was one of the main scientific processes that scientists were using computer science method for, and the process was firstly introduced by Fayad. So you can look up the reference, and it used to be described as all the steps that scientists need to produce in order to go from data into knowledge, and these steps were mostly selection of the data, processing of the data, transformation, data mining. That was what came before the current machine learning and deep learning methods, and then interpretation of and evaluation of the patterns. So in every step you do, you transform your data little by little. First you identify relevant information, then you pre-process your data, you transform them into something that you give to a data mining algorithm, and then you come up with patterns that then need an interpretation and an evaluation in order to become knowledge. Now, what we focused on is mostly this interpretation process. So the interpretation process, so the last step, the interpretation of the patterns, was somehow the core of the scientific process, was what would allow to transform patterns into knowledge. So to give a meaning to these patterns. This is actually how interpretation is being defined somehow in the dictionary. So it's really the action of capturing the meaning and conveying the meaning of something. Usually, the way you interpret patterns So the way you try to give a meaning to that and to capture this meaning is by using your own background knowledge. So you come up with patterns. You might have your own background knowledge, or maybe human experts in a topic that explain the patterns that the data mining algorithm has come up with. And that helps evaluating and interpreting this knowledge. The problem is this background knowledge might be missing. So you might require, maybe the expert doesn't know the actual explanation, or you might need, in certain use cases, you might need different experts from different domains. So gathering this background knowledge might be quite a time-consuming process. In this case, when this information is missing, the kind of hypothesis that we put forward was that symbolic AI, so symbols or knowledge graphs or linked open data, as we used to call them at that time, are another source of background knowledge. So the kind of idea that we had is, okay, if we have plenty of multiple of knowledge graph of data sources that are multi-domain, that are connected between each other. So at that time we had the linked data cloud. I think this picture is slightly later than 2013, but the idea is to have all these connected data sets that point to each other, and then you can serendipitously discover knowledge simply by crawling data sets one after the other. This information is most of the time it's connected, it's centralized in hubs and observatories. It's standardized according to certain vocabularies that allow modeling data, sharing data. So the vocabularies would allow to have interoperability across application. Then the kind of idea was, okay, maybe we can use all this information which is available online to help us explaining the patterns that an algorithm gives us whenever we don't have an expert in the picture, or whenever we are missing the background knowledge to explain that. And this is very similar to the idea that Newell and Simon already in the 70s had, so among the fathers in AI, that symbols were one additional layer to use when somebody wants to capture and convey the meaning. So you don't only need the data or the experience, but you need to put a structure and you need symbols on top of it in order to really get into an intelligent system that can understand and capture meaning. So based on this hypothesis, we set up a number of research questions. So the very first one we looked into was, okay, if we want to use if we want to use knowledge graph, large-scale knowledge graphs to generate explanations, we kind of need to understand what do we mean by an explanation. So we need a definition. Even if it's a working definition, we still need one. And then we kind of said, okay, we need a method that will allow us to generate explanations from knowledge graphs. So how are we going to do that? Then assuming we come up with such a method, we need to try to cope with all the problems that come with knowledge graph, including incompleteness, bias, noise. So the later research questions, obviously some of the research questions came out little by little throughout the process, right? So you look at your PhD from a different perspective, but somehow the later research questions were on improving the methods that we had in order to cope with the limitations of knowledge graph, including incompleteness and bias. And basically, looking now, I'm going to go through the research questions, but I don't want to dive too much into it. I mean, we have papers for that. And just the next slides are mostly to give you an idea of what the overall approach was. Starting with the definition of explanation, we first defined an ontology design pattern for explanation. So what we did was We looked into different disciplines. We looked into philosophy, we looked into linguistics, into social science, and we looked into their definition of explanations. And we noticed that even though there were different approaches and methods, explanations were always seen according to the similar characteristics. So there was always the generation of some coherence between old knowledge and new knowledge. The elements in an explanation were always the same. There was a theory, there were an anterior and a posterior event. There were circumstances that would make this event happening at the same time. And there were always processes. There would be one internal process where you come up with an explanation for yourself, and then one that is more an external process where you communicate the explanation to the rest of the world. And based on this, we then defined our own ontology ontology for an explanation, so our own definition that we could then feed into a system that would try to generate explanation according to these patterns. So we then just, it's a pattern in the sense that it can be instantiated in multiple contexts, but the overall idea was that you always have an event that happens before, an event that happens after. I'm not sure you see my pointer, but I hope so. There are certain conditions that make this event happening in a specific setting, and then there's some sort of theory behind, and an agent that outputs creates, conceptualizes the explanation. Based on this pattern, we then try to design a system that would try to use knowledge graph to generate explanation for a given pattern of data. And then the kind of question we try to answer is really, okay, if we want to use a knowledge graph, a very large knowledge graph, as background knowledge, which kind of process do I need to generate explanation? And then we try to work with some examples of patterns of data, of things that people might want to explain. We had this very good example that would work with Google Trends, and then you try to explain why a certain web search is regularly happening at specific points in time. So in these cases, why people are searching for the term "A Song in Ice and Fire" only in certain periods. So you see that there are very regular peaks. Or maybe we try to explain data like statistical data, for example, from the UNESCO. In this case, we have countries that are grouped according to the female literacy rate. And then you try to explain, okay, why is it, why is it happening that that certain countries have in common like a certain characteristic? And the very good thing is that we try to come up with a method that helped us working out these examples. And it was basically based on three main steps. One was an inductive logic programming step, where you try to compare positive and negative examples, and you have some background knowledge expressed in as triples, as facts about these examples. And then the goal is to induce the hypothesis that mostly represents your positive examples, which are the examples you want to explain. We used a knowledge graph search, so we try to search the linked data graph in order to find a common path, which would be expressed in terms of predicates, relationships leading to a specific entity in the graph. So we call this path. And then we would consider any path that is common to all the positive examples as an explanation for the group of positive examples. And then in order to improve the graph search, we implemented a greedy link traversal strategy. So we try to aim for the longer and longer path, and explore the graph using simple HTTP dereferencing in order to avoid computational costs. It was 2013, we still had issues of computational cost. And based on this method, we tried to answer mostly two questions. So first, we said, okay, which kind of heuristics
do we need to drive a greedy search and identify the best explanation? So we tried different strategies, and then one of the main findings for us was that a measure, so a strategy based on entropy, would lead to a higher explanation in less time. So we simply measure on what is the best accuracy of an explanation over time. So this is iteration in searching the graph. And we always ended up having the best, an entropy-based measure as the one that would perform best and give us the best explanation. This allowed us to come up with explanation for the use cases I was showing before. So why are women less educated than men in certain countries? And that's mostly when countries are least developed, for example. So they have quite a high human development index rank, and or they are defined in the Wikipedia as least developed countries. Or we had explanations like, okay, people search for a song in Ice and Fire whenever there is an event that is somehow linked to a Game of Thrones TV series. So we consider these as explanations, but of course, if you look at the results, you might notice things that are quite not right. And in particular, you look at these kind of examples. So it's true that if you have enough background knowledge about A Song in Ice and Fire, which is actually a book, and you know that there is a certain TV series related to that is based on this book, you know that the explanation for people being particularly interested in these is whenever the TV series is coming out. So there is a new season coming out, but there's nothing that relates the Tonga to the book, or basketball competition to the book. So the kind of questions we had to answer afterwards was really, okay, is there something in linked data that can tell us that Game of Thrones is strongly related to A Song in Ice and Fire, much more than basketball competitions or anything related to Tonga? So the second part of the method was really focused on strengthening this knowledge-based explanation. And we used a genetic programming algorithm to try to learn a function that could detect strong relationships between two graph entities that are quite distant in the graph. So we are not talking about two entities in the same graph, but you have one entity that is connected to another entity through hops in multiple graphs in multiple data sets. And then we really want to try to understand what is the strongest relationship. And what we did is that with a genetic programming algorithm, we tried to learn a function that could study the topological and semantic characteristics of the knowledge graph. So we really looked into how many hubs and how strongly connected was the graph, for example, which kind of vocabularies the graph was using. We gave all these to our genetic programming algorithm, and then we tried to come up with a function that would tell us, okay, this is a strong relationship, and we evaluated that against a human evaluated relationship path. And actually, what came out from this study was that the best thing for us would have been to try to follow nodes that would have quite rich descriptions. So here you have different examples of different functions that we tried, and then here you have the best performing ones. And the best functions that we could find were really the ones where focusing on following nodes with rich descriptions, that they would have quite a good number of namespaces. It was best to follow more specific entities, so really not hubs with many incoming links, but rather something that is more specific. And also we look into the SCORS vocabulary, and it was best to have fewer topical categories, so not something quite generic in terms of topic, but rather again a bit more specificity. Of course, we had to look into the bias in the data as well. So the results were not optimal. And as I said, we needed to deal both with incompleteness of the data, but also with inner bias of the data. And then what we tried to do was to use identity links. So remember that we are still talking about linked data, where data sets are connected to each other through identity links, including same-as. And what we tried to do was to measure the bias in a given data set by comparing the projection on one data set into another one. So the overall idea was really that you have a data set, which could be, I don't know, the linked movie database, and you have a certain amount of entities that are connected through the DBpedia using identity links. And the projection of the movie database is mostly the set of entities that in DBpedia that are connected to the movie database. And then we would basically compare all the entities in the larger data set with a subset. And using some correlation tests, so some t-test, and by comparing the distribution of property value pairs between the subset of the entities and the large set, we try to identify which were the bias in a given data set. So, for example, I would recommend you to refer to the paper, but what we discovered was, for example, that the linked movie database was particularly focused on black and white movies, and that certain digital humanities datasets were focused on poets and novelists from the 18th and 19th century. So it was a way to try to measure the bias in the datasets that we were using to generate explanations, and once we learned this bias, we could also try to somehow input this information in our system and generate better explanations. Now, this was quite a long journey that ended up in 2016, and there's a number of things that happened since then, what I call the present. So I don't have enough time to focus on everything, but I chose 3 particular aspects that I'm going to show, which help us also thinking a bit further into the steps that we want to take afterwards. The very first thing, of course, is the rise of deep learning. So when we started the work on explanations and knowledge graphs, actually on knowledge graphs for explanations, deep learning was probably just booming, and I wasn't even aware of that. So what we were talking about was using knowledge graphs to generate explanation for outputs of any machine learning algorithm. But we've never heard of deep learning. I think, maybe the first papers are around 2012, but if I'm not mistaken. But of course, the hype came much later. And the DARPA, so deep learning and all the methods that came with deep learning showed impressive results that could achieve say the same results as human would, and but also showed a number of limitations. So the facts like the Cambridge Analytica scandals or the loan accreditation scandals showed that these systems were not able to show a clear reasoning, so the reasoning was quite opaque. These systems were data hungry, so you needed a lot of data to train them. They were too brittle in this sense. And then DARPA came out with this Explainable AI program that was 2016, if I'm not mistaken, on, okay, let's try to implement, create systems where the user is, that are transparent, that can explain the machine learning model, and then where an explanation can be given on why a certain output is being given. So this need of explaining the models and the results really came out, and we started seeing methods like SHAP and LIME, which are probably the most basic ones, and then there's a number of other systems that came out afterwards that could tell you, okay, the most important features to come up with an explanation in your data set are so like maybe the race or the occupation of your data. Or we started seeing saliency maps, okay, with image recognition. What are the most important parts that a system focuses on when generating explanations? These, especially the explanations in the explainable AI area, and if you look into the major AI conference, you start seeing a boom of. I think explainable AI became an actual topic or a subfield in AI. One of the questions that people ask was, okay, are these explanations that SHAP and LIME come up with, are they really working, especially in a real world context? So they do work in a small use case, but what if I apply it into a real world context? And somehow the neurosymbolic field, which was already in the meantime developing on his own, came up a bit in the rescue of this problem. So somehow we started seeing methods that try to combine a symbolic approach, so symbolic reasoning with neural network, either to maybe improve the explainability and trust of a system using a symbolic description, or by creating a sort of hybrid interaction between the neural network and the reasoning system. So these are just two of the many examples that you could see when where the knowledge graph worlds try to jump into the explainable AI world and say, okay, hey, look, we should be maybe using knowledge graphs and ontologies to help. We also did part of this. So what we try to do, this I completely forgot the reference to this work, but we published in 2021. We really try to say, okay, if many people are looking into using knowledge graphs as a tool to explain machine learning methods, let's try to look at what's the state of the art. So how are people in machine learning using knowledge graphs? What are the most important characteristics? So we try to look into different tasks and different areas, and we try to look into the characteristics of the knowledge graphs, the characteristics of the model, and the characteristics of the explanations that we were generating in order to come up with a picture of the field. And this is more or less what we came up with. So we learned certain things, like if you are dealing with tasks for recognition and recommendation, most of the explanation you will get are really about the model and how it behaves. And most of the information that is being used from the knowledge graph is the assertion box. And whenever we deal with tasks that involve the interaction of the user, like conversational agents or recommender systems, the knowledge graph information is used more into the training of the model to generate a certain explanation rather than as a post-hoc step. We looked into the different types of knowledge graphs, whether they were factual or common sense or domain knowledge graphs, domain specific. And it turns out that common sense knowledge graphs, there are not that many, but they were being used for image recognition and question answering. We also look into the reuse of knowledge graphs. So we've been talking so much in our field about reusing knowledge graph, reusing ontologies, and we kind of ask, okay, is this being applied in this field? And it turned out it was quite an established practice. So very few were coming up with their own knowledge graph. Most of the methods were using DBpedia, Wikidata, ConceptNet, or a combination of them. Actually, we looked into whether these methods were using only one knowledge graph or multiple ones. And we were hoping to see a bit more, but it does happen sometimes in NLP tasks. And really the kind of, this is the kind of picture that came out. So if certain areas are more focused on model embedded knowledge, so explaining the model rather than explaining the outputs, certain others are more focused on using the ontologies of the knowledge graph rather than the facts, and so on and so forth. So I think the analysis we did is around 60 papers, more or less. And we kind of try to identify also the challenges for the field, right? So there are things that we were hoping to see, but that didn't happen, including what we call the co-creation of explanations, so really having a sort the human having a role into the generation of the explanation. There are issues related to the maintenance of the knowledge graph. So how to deal with missing information or bias when coming up when generating explanations. And of course, this is a problem that we also saw during in the PhD. And also there are issues related to the automated extraction of relevant knowledge when using a knowledge graph that generates explanations. So most of the methods that we analyzed, when coming up with an explanation, end up manually selecting the relevant information to generate an explanation. And this is quite something. It means that there's still a lot to do in the field in order to move forward. So this was one part of the story. So what happened ever since deep learning? There's also the field of hybrid intelligence that came up. So I don't know if many of you heard about hybrid intelligence. Maybe you heard about human-centric AI. This is another way of addressing this problem. The overall idea was that there is an emerging field in AI, and it's emerging because you start seeing different conferences and workshops around the topic. There's a number of national and international collaboration networks that are really focusing on this concept of hybrid intelligence, and the overall idea, because we don't really have a proper definition, but we do have a working definition of hybrid intelligence, is to have to aim for AI systems that try to enhance human capabilities, as other scientific tools would do. Think of the telescope that allows a scientist to look where his own eyes cannot see, or the machine, the car or the airplane would allow people to reach places that they couldn't reach easily with their feet. So it's really about seeing AI system as an extension of the human intelligence, rather than seeing AI as a tool that replaces us. So in this sense, hybrid intelligence really look into systems that collaborate with humans, aiming for a complementarity. So weaknesses and strengths of both AI and humans are complemented by each other. And really about this synergetic idea. So the mixed team, the hybrid team, is aiming for the same, has a shared goal. This is so we have a research agenda. I'm part of the Dutch Hybrid Intelligence Consortium, and I've been part of the Hybrid Intelligence conference of in the past years. And it's a really vibrant field. And explainability, explaining is also a part of the research agenda. So it's not only about trying to collaborate, but how in this collaboration, the goal is also to try to communicate our own intention and explain our own actions and our own reasoning. So one of the core topics that we established when hybrid intelligence came into the picture was really on how to create systems that are able to deliberate and explain to their collaborators. I'm more than happy to discuss this a bit further. And somehow, as part of the hybrid intelligence picture, we also, and as part of the contribution that we could give with ontologies and knowledge graphs, with respect to explainability, we also try to work on a number of what we call boxologies or terminologies for hybrid intelligence, to establish mostly to establish a shared language between agents in a different team, agents in the same team that would collaborate between each other. What we did in one of the newest work was really on comparing different hybrid intelligence scenarios, and first trying to identify what are the common knowledge roles. So we came up with a high-level ontologies of agents, interaction types, and specific scenarios. And we try to also identify, using these high-level ontologies, what were the most specific hybrid intelligent tasks, including ones that would relate to creativity and explainability. And then on the side of it, we would have tasks like team awareness and multimodality. That's the second part of the picture. So we talk about deep learning, we talk about hybrid intelligence, and what also came into play with respect to explanation, and we didn't have that much time to dive into it, but hybrid intelligence is strongly related to that as well, is really on, especially with a European perspective, is really on the GDPR and EU AI Act, which recently came up. But really the idea is to try to monitor the systems that we are developing to make sure that users are protected, both in terms of the data that are being generated and the methods that are being generated. And this also means to be able to explain the reasoning and to trace back the information that is being output. So explainability and transparency became started appearing together in the picture. So if you want transparency, you need to be explainable, therefore showing your reasoning. And now with this EU AI Act, the idea is really that there are certain obligations, there are certain systems that need to show some transparency. They have transparency obligations, so they need to be able to explain why certain things are happening. Otherwise, they are considered unacceptable. This is a very, so I have a few minutes left. I think this is a very quick overview of what has happened ever since, which leads us back to, okay, what is going to happen now and how can we kind of think of everything that has happened so far, and where are we going to go? Of course, I couldn't get away without mentioning language models at least once. So somehow one of the questions that one might ask, and we also kind of wondered, was, okay, but everything we've done, could this be now done? So the overall knowledge discovery process could just be replaced by language models, by large language models, by LLMs. Could we just not replace all the steps or the explainability steps? Do we actually need knowledge graphs for that? And it's true that LLMs, language models, are very good in dealing with noise and inconsistency, and like the methods that we had before were not that much able. They allow us to extract information very quickly from large structured data. So that goes towards the dream of doing a web scale learning, or one could argue they already achieved that. They're actually quite good in capturing some complex semantics. So somehow it has been demonstrated that defining a class can be with specific boundaries. So the boundaries of the definition of a class is quite difficult, are quite hard. So there is no universal class description. And especially with the embeddings based methods are able to capture this complexity quite a bit better, and of course are very good in generating natural language. So instead of generating explanation in a mechanistic way from the triples, they are able to generate a much more human-friendly explanation. The problem is that they are still limited in a number of things. So learning from rare and unique events, especially like the ones that you can find in the web, is still quite difficult. These methods are not yet able to show proper reasoning and argumenting behind creating a thorough argumentation behind what has happened, and also they don't really deal with fairness and interoperability, acceptability, all these fair aspects that we've been looking into as knowledge graph community are not yet part of the picture in a language model. So somehow there are limitations in using that, but it doesn't mean that we need to discard them completely, but we can just join the both words and work out something to generate better explanations. So I want to conclude in the last few minutes to really think, okay, if we now look at knowledge graphs and whether they're useful to generate explanation and do they actually work, what is it that we learned? So somehow, both based on the PhD and everything that happens afterwards, yes, we can use knowledge graphs, but they are mostly an intermediate representation. So knowledge graphs are really for the machine consumption. They shouldn't be for human consumption. And the RDF is just a language for machines to perform an exchange of information which is unambiguous. So we should really not look into knowledge graph as something that we humans should understand, but more as something that machine can quickly exchange. We can use knowledge graphs to gather content to generate explanation, but really the graph structure is just the backbone. So we don't really want to use the knowledge graph to create an output. We can use language models for that. But we can use knowledge graph as to gather the backbone of the explanation, which can then be output according to different users in a different dimension. So we think, okay, an expert user might need a longer explanation, with more arguments, and then a non-expert, a layman, might need a much shorter and simpler explanation in terms. And LLMs are great in doing that. You can ask them to rephrase a certain concept according to different dimensions. Also, knowledge graphs allow to check to trace back information. So you can really walk down the graph and check whether the information is truth. And this is quite this is much better than looking into the propagation of the activation of a neural network and try to decode what does it mean in order to come up with an explanation that you might not be able to explain that clearly yourself. And finally, scalability, which was part of the picture at that time. Okay, how can we deal with very large knowledge graphs, and we want to integrate as much knowledge as possible? Well, actually, this is not that relevant anymore. And what people are really aiming for, and we also saw this when collaborating with industries, it's much better to have a high quality knowledge graph, which is curated by the expert, to generate explanations rather than having a very large knowledge graph. So this is one part of the story. And then the other part is more of the big picture. What we learned is really explainability is not only about machine learning. So in hybrid intelligence, we deal with explainability, we deal with experts from all kinds of fields, from social science to computer science, and people look into explainability from different in different ways. So it's a bit of a jungle of terminology. We cannot really agree whether what we mean by something being explainable, and then we need to try to find a way to harmonize that. We learned that explanations are really task dependent. So yes, we have an ontology design patterns for the explanation, but we need to adapt this according to the context. And again, we can use language models for that, but it's the target audience or the language or the type of explanation really need to change according to the situation. And more importantly, we need to look for the human. So knowledge graphs are only one part in the explanation process. So in order to generate explanation, you need a knowledge graph, you need a subsymbolic method, but you also need a human that interacts with the system. Because in the end, as we said at the beginning, explanation is a social process. It's a dual process. So it has to happen in a co-creation setting where the user is really interacting with the system to come up with an explanation he's satisfied with. And in this sense, we also need interdisciplinarity in the picture to try to measure whether an explanation is interesting or not. So we don't only need a computer science perspective, but we also need to try to integrate the talks that we have with social scientists and cognitive scientists to make sure that the explanations that are being generated are actually useful. So to give some ideas on what, and then I'm just done. I know I'm over a bit. What we suggest is that really we should look into the kind of knowledge in artificial intelligence. So some people have called this knowledge science. Some people have called it empirical semantics. We call it knowledge in AI. So we really need to go back to the empirical analysis of the knowledge graphs that we create and we deal with. We need to understand their modeling style and the kind of semantics they're communicating, and whether the semantics is enough or too much to generate explanations. We need to check for the usefulness and limitation of the knowledge graphs and the knowledge that we create. And somehow we need to try to move from the step of, okay, how can we fit knowledge into the learning process? This we know how to do it, or at least we have good methods, but we really need to focus on which kind of knowledge we need to fit in order to be able to learn something and to generate explanation, for example. So somehow this is a call for the community to start. So where do we start? And I have tried to revisit a bit the research questions that I had in the beginning, thinking, okay, based on this idea of knowledge in AI, then maybe we need to try to fit the explanation pattern into the existing systems. We need to try to come up with explanations that, like using deep learning and at a web scale. We need to try to augment explanations and turn them into complex narratives. We mentioned these complex argumentation. And for these, we can really combine knowledge graphs and language models. And we really need to compensate whatever information is missing by performing a co-creation of explanation with the humans. This is the end of my talk. I thank you so much. I don't know how many people are there. I thank you so much for taking the time to listening to me. I thank Tobias, Antoine, Olaf for inviting me. There was an amazing opportunity. I invite you to reach me out for exchanges, and I really hope to see you at the next Hybrid Intelligence Conference in Sweden in June. This is the end of my talk. Thank you.
All right. Thank you, Ilaria. I should buy one of these sitcom applause machines and give you a round of applause that reflects the size of the audience that we had. There were a few questions already in the YouTube chat, so please keep them coming. And in the meantime, I will pose some of them to you. And if there are no more questions, I may ask the people have to deal with mine. Good. So let's start. There is a question by Mevish on the chat, and she's asking, what is your vision on using your explanation techniques for large language models? So do you think the same techniques are useful for them as well, or do you need a different kind, or is there a way of adapting maybe the methods?
Yeah, thanks. So this is a very good question. Of course, I mean that's the kind of question I'm expecting in these days, because we do have language models are able to achieve so much that it's hard to think, okay, if I done everything wrong, can they just do better than me? And I mean, I would be very curious to just do a simple comparison. I like this question a lot. So the question is really, can we use these techniques with large language models? Because I now have a number of PhD students working on this, and we were discussing this just this morning. You certainly have the advantage that you might not need to crawl the knowledge graph anymore to generate explanation. So all the problems of heuristics to search the graph, to reduce the computational complexity might not be needed anymore. With that said, I still think that you need to combine language models and knowledge graphs in order to be able to trace back the information. And especially if we are talking about truthfulness of an explanation, I can ask my knowledge graph the language model to come up with an explanation for a given pattern of data, but I also want to make sure that I can trace the provenance back. And this is something that I want to know. I mean, probably a knowledge graph is much better to do than a language model. So I still think that, as I said, the backbone of the information should come from a knowledge graph in a way that you can reconstruct the subgraph somehow that generates your explanation, and then the output form it can be generated or situated according to the users by the language model. That would be my answer.
Okay. So thanks for that. There's another question by Peter Jones. He's asking, to what extent do you think AI and explainable AI may reduce or undermine the use or development of domain-specific languages?
Sorry, I lost the second part of the question. So do I think?
AI and explainable AI reduce the use of domain-specific languages?
Well, I don't think they actually, I'm not quite sure whether by domain-specific language, we mean domain-specific representation, or so domain ontologies. But I don't think they actually reduce it, or at least I don't think they should reduce it somehow. I see more an integration of the two, in the sense that the same way there are these methods that use. So I've seen methods using domain-specific ontologies to come up with maybe decision trees about an explanation that is being generated. So they the advantage of domain-specific language is still that they are curated by the experts, and so they are still more reliable. So the two methods should kind of I don't want to think of explainable AI methods as taking over, but rather to try to complement, to combine the two more in a neurosymbolic fashion.
Mm-hmm.
I hope this answered the questions.
Hi, yeah, I hope so too. Speaking of, maybe this goes into the direction of one of the questions that I had noted. So if we have a domain-specific language or a domain-specific way of modeling things, then this allows to very concisely write down things for a specific domain. Previously, one of your explanation methods, you used something that was looking at graph distance in a graph, right? And if you change, if you have something very good for one domain, then that obviously changes the distance in the graph. So maybe you can reflect a little bit on how the graph structure or the role of how things are modeled, or how much entailment is applied on the graph changes the diameter, the distance, or the results of your approach.
Yeah, so I think in general, this is the kind of problem we try to approach both. So with a follow-up method. So when we looked into trying to identify strong relationships, but also trying to cope with the inner bias of the information, the assumption. So we've never dealt with knowledge graphs we created, right? So we always dealt with knowledge graphs that were created by others. So the assumption was you might not find the information that you might need. And you need to, so sometimes the information is very well curated and sometimes this is not. And somehow we need to find a way to cope with this problem in order to be as generalizable as possible. So my view is really that there is not a universal way of, so there is not a method that can deal with both. The most important thing is being able to cope with the problem and integrate it in the methods that you develop. So you need to be aware that information might be missing, and you need to make sure that your method compensates for that. This can happen inside the development of your method or as a postdoc, like a posteriori step. And it can be as simple as, I mean, in the same view of the co-creation with the user, it can be as simple as, okay, let's interact and see whether I'm missing some part of the information. So somehow one of the reasons why we had to look into the strength of the relationship was also because we were missing these, and we had to find a strategy to survive in this.
Okay. There's another question from S. Kimstar, and they are asking, what adaptations do you see for knowledge for this whole set of approaches to deal with multimodality?
Sorry, so
you had like, there was this with the cat picture where there was some computer vision aspects in it, and maybe you reflect a bit on multimodality when it comes to the approaches you presented.
It's true that we've never, the kind of knowledge graph we've been dealing with, and multimodal knowledge graphs were not really that common at that time, I think. So it's true that one aspect that would be interesting, and maybe we didn't discuss this as in the future step, but it is in these days we are now talking about. We hear much more about multimodal knowledge graphs. We hear also about knowledge graphs that somehow try to integrate the physical world. So like we deal with robots in some scenarios, and we also have this problem of, okay, I have a knowledge graph that has to integrate both abstract concepts, but also the physical world. So I think it would be quite interesting to think on how to generate explanations that are multimodal in this sense. This is one part of the answer, in the sense that, yes, we didn't look into multimodal knowledge graphs and it could change. The other part of the answer is the explanation that we could generate. So the kind of patterns that were coming out could also be patterns coming from multimodal data. So like I dealt a lot with clusters of data points, but these data points could as well be paths of an image, for example, that will represent I don't know, the ear or the tail of a cat, this kind of thing. So I didn't deal with that concretely, but it could. I don't see why the method shouldn't work on image labeled with specific information that we might want to explain. So that, say, with respect to multimodality, there are these two parts. So the original method would probably work also on data points coming up from multimodal data. And then the multimodal knowledge graph, we didn't look that much into it, and it could be quite interesting to look into multimodal explanation in this sense. So that's
okay.
fine.
Thanks. So maybe as a last question, jumping back to your history, and because this is the cost action on distributed knowledge graph, where we care about distributed and decentralized things. So you had this one approach that was based on dereferencing of URIs and looking at things from that perspective. Now, you kind of gave me the impression that you say, okay, now the person who developed the large language model did the web crawling for you, but maybe you can say something like, all the methods that you have developed in the meantime, after you were done with dereferencing URIs, are they based on a global kind of view to, I don't know, generate embeddings and things, or would they still work in a distributed and decentralized setting?
I guess as long as so the embeddings are convenient because they can embed a lot of information in a very small space. And that's something that we didn't have, so we had to come up with a dereferencing opportunity. But also, we didn't want to deal with storing the graph, because if you store the graph and you query it, then you need to know the data model, and we didn't care about it. So what we really cared about was this kind of serendipitous hop. I remember one of the first papers I saw was something Olaf also did on navigation and query languages. So that was quite related. So I think the most important, the part that would still work is, even in a distributed context, is as long as you have connections or pointers from data to data, then it's fine. It doesn't really matter. And we didn't care whether it was the web of data or it could have been the load stored in an HTTP file. That was really not the problem. The main problem was where is the relevant information? How do I identify the links between that? And this is valid in any context. Whether I have the information centralized or decentralized, I would say. Then okay. I never really experimented with that, so I can't tell. But
good. Yeah, thanks for the answer. I don't have more questions from the YouTube chat. With that, I just want to thank you again for the very nice talk and the very nice Q&A session. Before we close the stream, I can only advertise the next talk on January the 31st at the same time as today by Mayank. You can check out our website and follow us on this thing formerly called Twitter. And of course, you find all the recordings of our talk on our YouTube channel.